Hello, in this video we will look at how to use the formula for continuous growth to solve a question about half-life. There are two special formulas, half-life and double in time. They can both be used in addition to the continuous growth formula. But the continuous growth formula is what both of those formulas are based on. And we can use continuous growth formula instead of either one of them. So instead of memorizing three formulas, we can only remember one continuous growth formula, and it works for all the cases. All we need to do is do two steps. They are the same two steps, and then we will get the answer. So in this example, let's look at how to do that. So here is a situation. Let's say we have a half-life of a radioactive isotope F13, which is fake 13, is 13 years. How long will it take for a sample of this isotope to decay to 30%? So this question at first appears that there is not enough information. The formula for continuous growth is final amount is principal e to the rate times time. We are not given the principal. We don't know what we start with. And in this case, it doesn't matter. We can choose any number for the initial amount. Let's say 1 gram. And as long as we use it consistently, 30% of 1 gram is 0.3. Half of 1 gram is 0.5. Or another good number to use is 100 grams or 100 milligrams, because half of 100 is 50, 30% of 100 is 30. So let's use 100. Let's suppose we started off with 100 milligrams, and that would be our principal. Well, if we did that, then step one is we find the rate. So if we assume that we start with 100, and then our half-life is 13, which means in 13 years, our amount will go to half, which is 50. The only thing unknown is rate, and we can find the rate, which is what we're looking for. So to get to the rate, we need to undo multiplication by 100. To do this, we divide both sides by 100. That makes 0.5 equals to e to the 13r. And this is exponential question, and to solve it, we use logarithms. So we have logarithm base e, and then the input and the output switch place. And the only thing now is logarithm base e is ln, natural log, and the only thing left to do is undo multiplication by 13. We divide both sides by 13, and this is the rate. That's the end of the first step. Let's put that number in the calculator to see what the decimal actually is. So here is natural log of 0.5 divided by 13. So our rate is negative 0.05, and usually we use at least 3 decimal places. 5 decimal places would probably be better in this case. Anytime we deal with exponential, it is better to keep more decimal places. So that's our growth rate. Step 2. Now that we know the growth rate, we answer the question. How long does it take to get to 30%? Well, if we start off with 100, and we now know the rate, the only thing left is time. 30% of 100 is 30. So once again, the same setup. Unknown happens to be is in exponent, and so to get to it, we use logarithms. First, divide both sides by 100. That makes 0.3 is e to the negative 0.0533, and then natural log of 0.3 is negative 0.0533t. Dividing both sides by the decimal, we get our final answer. So here, using the calculator, let's find out what that is. And we will use all the decimals in this case. So natural log of 0.3, and then if I press second answer, I will copy, first I need divide. divided by the second answer, and the answer is 22.58. So the final answer is 22.58 years, or approximately, let's say, 22.6 years for our sample to decay to 30%. And that's it, that's the final answer, and that's how to use the two-step process to solve any question that has to do with half-life or doubling time. Now, the reason we used the decimal, we keep 5 decimal places as opposed to, let's say, 2 or 3 when we deal with exponential, is because with exponents, they are very sensitive. So if we don't have enough numbers, the answers could be very different. So just for illustration, let's type in this last part, ln of 0.3, but now we're only going to round it to 2 decimal places. So if I type in ln of 0.3 divided by negative 0.05, the answer now becomes 24 years. So the difference is now in 1.5 years, just by changing a few decimal places. So that's why we keep more decimals when we deal with exponents, because there is a big difference between these two results. And that's it for this video. If you have any questions about anything, please let me know. Thanks a lot for your time. Take care.